For most people, artificial intelligence begins with a prompt on a screen. But behind every response is a vast physical infrastructure that few ever see. Long before today's AI boom, Microsoft recognized that the next generation of data centers would require far more than faster servers. They would need a new approach to reliability, resilience, and energy. That realization sparked an engineering journey that began in 2018. One focused on exploring whether hydrogen fuel cells could one day provide clean, dependable backup power for the world's most demanding computing facilities. Artificial intelligence is transforming every industry, but its rapid growth comes with an equally dramatic increase in electricity demand. Every AI model, every cloud application, and every real-time calculation depends on thousands of servers operating continuously. Those servers cannot afford unexpected interruptions. As AI workloads become larger and more complex, the challenge extends beyond computing performance to ensuring there is always enough reliable power to keep these systems running around the clock. Meeting that demand requires far more than simply generating electricity. Power must travel through an intricate network of transmission lines, substations, transformers, switchgear, and distribution systems before reaching the servers inside a data center. As AI campuses continue to expand, every part of this electrical chain is being pushed to deliver greater capacity with uncompromising reliability. The future of artificial intelligence depends not only on better software, but also on stronger and more resilient energy infrastructure. Reliability has always been the defining requirement of a modern data center. Even a brief loss of power can interrupt critical services relied upon by businesses, governments, and millions of users worldwide. To prevent that from happening, multiple layers of backup systems stand ready. Batteries provide immediate protection while longer duration backup generators take over, ensuring operations continue without interruption. For decades, diesel has fulfilled this role, but Microsoft began asking whether another technology could provide the same reliability while addressing future sustainability goals. Hydrogen fuel cells emerged as one possible answer. Unlike diesel generators, fuel cells produce electricity through an electrochemical process rather than combustion. Hydrogen combines with oxygen to generate electrical power while producing water and heat at the point of use instead of exhaust gases. The concept offered an opportunity to rethink backup power, not by replacing proven engineering overnight, but by carefully evaluating whether hydrogen could eventually become another dependable option for mission-critical infrastructure. Microsoft's program followed a deliberate engineering path rather than a rapid product rollout. Initial demonstrations proved that hydrogen fuel cells could support a single server rack. The company then expanded testing to larger systems capable of powering entire rows of servers before progressing toward multi-megawatt prototypes that approached the scale required for commercial data centers. Each stage answered new engineering questions, building confidence through measured experimentation instead of assumptions. At the center of every hydrogen fuel cell system is the fuel cell stack. Inside, hydrogen enters one side while oxygen from the surrounding air enters the other. A proton exchange membrane separates the reaction, allowing protons to pass through while forcing electrons to travel along an external electrical circuit. That movement of electrons creates usable electricity, while sophisticated materials and carefully engineered flow channels maintain efficiency, durability, and consistent performance throughout the process. The fuel cell is only one component within a much larger energy system. Hydrogen first moves from storage into the fuel cell, where electricity is produced before passing through power conditioning equipment and the uninterruptible power supply. From there, electricity reaches the AI servers that perform the computing work. At the same time, cooling systems remove heat, while water management maintains stable operating conditions. Every subsystem works together, forming a carefully integrated architecture designed to deliver reliable power whenever it is needed. The science behind a hydrogen fuel cell is remarkably elegant. Hydrogen molecules entering the stack are separated into protons and electrons. The protons move through the membrane while the electrons travel through an external circuit, generating electricity that powers connected equipment. On the opposite side, oxygen combines with the returning protons and electrons to form water, while heat is also released as part of the reaction. This direct conversion of chemical energy into electrical energy is what makes fuel cells fundamentally different from combustion-based generators. Turning that chemical reaction into dependable backup power requires far more than a fuel cell alone. Hydrogen storage, fuel delivery systems, Power electronics, cooling equipment, control software, safety systems, and electrical distribution must all operate together as one coordinated system. Microsoft's demonstrations were designed to evaluate how these components interact under real operating conditions, ensuring that every part of the architecture performs reliably before larger-scale deployment is considered. Scaling this technology involves much more than building a larger fuel cell. As power output increases from kilowatts to megawatts, every supporting system must also expand. Larger hydrogen storage, more sophisticated cooling, higher capacity electrical equipment, stronger control systems, and additional safety measures all become essential. Microsoft's engineering approach demonstrates that scaling backup power is really about scaling an entire ecosystem rather than a single piece of equipment. Engineering confidence is earned through testing. Every demonstration provides valuable information about startup behavior, electrical stability, thermal performance, system efficiency, and operational reliability. Engineers monitor how each subsystem responds under different conditions, identifying opportunities for improvement before progressing to larger installations. This careful process reduces uncertainty and helps determine whether hydrogen fuel cells can ultimately satisfy the demanding reliability standards expected inside hyperscale data centers. A successful backup system must integrate seamlessly into the existing data center environment. Fuel cells must communicate with power management systems, batteries, switchgear, monitoring platforms, and cooling infrastructure while meeting rigorous operational and safety requirements. Hydrogen detection, ventilation, emergency shutdown procedures, and continuous monitoring are all essential parts of the overall design. The challenge is not simply generating electricity, it is ensuring that the entire facility continues operating safely and reliably during unexpected events. Hydrogen offers several characteristics that make it attractive for backup power applications. Fuel cells operate quietly, produce electricity without combustion, and generate water and heat at the point of use. They also have the potential to provide long-duration backup beyond what batteries alone can deliver. At the same time, their overall environmental impact depends on how the hydrogen itself is produced, transported, and stored. Evaluating these advantages and limitations is a critical part of Microsoft's ongoing engineering program. Every energy technology involves trade-offs. Diesel generators benefit from decades of operational experience, established supply chains, and proven reliability. Hydrogen fuel cells introduce new opportunities, but also new engineering challenges involving infrastructure, cost, storage, maintenance, and fuel availability. Microsoft's objective has never been to declare an immediate winner, but to understand where hydrogen can provide practical value within the evolving landscape of AI infrastructure. As artificial intelligence continues to grow, backup power becomes even more important. Future AI facilities will require electrical systems capable of supporting increasingly dense computing loads while maintaining uninterrupted operation. Hydrogen fuel cells represent one possible pathway toward achieving that goal, offering another option alongside batteries, conventional generators, and emerging energy technologies. Microsoft's work is helping engineers understand how these systems may contribute to the next generation of resilient data centers. That journey is still underway. Each new demonstration provides additional insight into fuel cell performance, system integration, operational procedures, and long-term reliability. Rather than rushing toward widespread deployment, Microsoft continues to evaluate the technology through careful engineering and incremental progress. Every test brings the industry one step closer to understanding whether hydrogen fuel cells can become a practical component of tomorrow's AI infrastructure where reliability remains the highest priority. Despite years of successful engineering demonstrations, hydrogen fuel cells have not yet become Microsoft's standard backup power solution for data centers. That isn't because the technology has failed. It reflects the reality of deploying infrastructure at hyperscale. Before any new backup system can replace a proven technology like diesel, it must demonstrate consistent reliability, economic viability, operational simplicity, and the ability to integrate across hundreds of facilities. Microsoft's program shows that technical success is only one milestone on the path to commercial deployment. Several important challenges remain before hydrogen can be deployed at scale. The availability of low-carbon hydrogen varies by region, while storage, transportation, and refueling infrastructure continue to evolve. Capital costs must become more competitive and maintenance practices need to mature alongside the technology. Every component, from hydrogen production to on-site delivery, must perform with the same dependability expected of today's backup systems. Solving these challenges requires not only better equipment, but also stronger supply chains, industry standards, and supporting infrastructure. Even so, Microsoft's work is already shaping the future of resilient AI infrastructure. Each demonstration expands engineering knowledge, improves system integration, and helps identify practical pathways toward larger deployments. Whether hydrogen becomes a primary backup technology or part of a broader hybrid energy strategy, these projects are establishing the technical foundation for future decisions. They remind us that infrastructure transformation begins long before commercial adoption. It starts with disciplined engineering, careful testing, and the willingness to explore new solutions. Microsoft's progress has attracted attention across the technology industry because every hyperscale operator faces the same challenge: delivering reliable power to support rapidly growing AI workloads. As computing demand continues to accelerate, companies are evaluating multiple approaches, including advanced batteries, fuel cells, microgrids, and alternative backup technologies. While the solutions may differ, the objective remains the same: building data centers that can operate continuously while adapting to the changing demands of energy, sustainability, and digital infrastructure. The future of AI infrastructure will likely depend on a combination of technologies working together rather than a single breakthrough. Grid electricity, battery storage, intelligent controls, renewable generation, and long-duration backup systems each contribute to overall resilience. Hydrogen fuel cells may become one important piece of that larger architecture, particularly where extended backup power is required. Microsoft's program demonstrates how modern data centers are evolving into highly integrated energy systems designed to support increasingly sophisticated computing environments. History shows that every major technological revolution has required a corresponding transformation in infrastructure. The expansion of artificial intelligence is no different. Behind every new AI application lies an enormous investment in power systems, cooling networks, communications infrastructure, and backup generation. As demand continues to rise, engineers are rethinking how these systems are designed, connected, and operated. The future of AI will be shaped as much by advances in infrastructure as by advances in software. One of the most valuable lessons from Microsoft's hydrogen program is that no technology operates in isolation. Fuel cells depend on hydrogen production, storage, distribution, cooling, power electronics, monitoring systems, and grid integration. Understanding any single component requires understanding the entire system surrounding it. That systems-level thinking is becoming increasingly important as AI infrastructure grows more complex, reinforcing a simple principle: to understand the future, we must always follow the system. Microsoft's hydrogen journey is far from over, and neither is the transformation of AI infrastructure. What began as a small engineering experiment has grown into one of the industry's most closely watched programs, exploring alternative backup power for hyperscale data centers. Whether hydrogen ultimately becomes a standard solution or remains one option among many, the program has already demonstrated the value of rigorous engineering, long-term testing, and continuous innovation. As artificial intelligence reshapes the digital world, the hidden infrastructure supporting it will continue to evolve, and understanding those systems will be essential to understanding the future itself.